So this session is about debugging TLS issues in Wireshark. It's mainly focused on the application layer point of view. So I will probably not go into like timing issues or performance issues, but focus on the TLS and application. So a bit about me. I started contributing to Wireshark in 2013 and became core developer in 2015. I started in, well, the TLS sector, and that's basically where my interests lie, TLS, security, and do things all over the place. I work at Cloudflare in the crypto team, and well, yeah, there I'm also using Wireshark a lot to develop new TLS features. So I'll start with, I'll try to walk you through to one issue I've been using Wireshark for. It was a bug in Firefox. So the problem was whenever I tried to add a new attachment to a bug, well, I would open the attachment page, I would select my packet capture file, and then I'll try to type a long description, and then later I realized, like, oh, I should actually shrink my capture file, like filter away some stuff. Well, when I did that, and when I submitted the form, I suddenly saw this like very strange white page saying 400 bad requests. This is not what I was used to. Like when typically on a Cloudflare enabled website, when something goes bad, you see this like very nice, colorful page saying it's the origin issue, it's somewhere in the middle, or it's you, the browser. So this was kind of scary, and I was wondering what exactly went wrong, whether there was like a bug in, for example, the edge, like Cloudflare, or somewhere else. So when encountering such issues, it's always good to have a way to reproduce it. So you start with the problem description, which I just provided. You will also include the environment where it occurs in. So in my case, I tested. I was using Firefox 61 on Linux. Perhaps it occurs on all the platforms, but this was the one that I found the issue with. And then the steps to reproduce was basically select a file, modify the file contents, like make it smaller or make it larger, without like selecting the file again, and then actually submitting the button. And the expected result was, well, the bug tracker should accept my submission and propose a new comment and so on. The actual result was, well, not exactly as expected, a white page. So at first I was like, okay, this is a website. Let's try to open the web developer tools. So I press like F12 in Firefox. I go to the network tab, and then repeated my steps to reproduce. And that triggered some, well, requests, and this is how it's supposed to look like. So there's some kind of status code, like turned OK. It recognized the remote address I'm talking to, basically the address of bug.wireshark.org, and because it was able to load stuff, it could also load some style sheets, script, and so on. So remote address, status code, and so on. The expected result. Instead, I got something that didn't make sense at all. It said, so previously it would report the size of response headers, and so here it would suddenly say something like, oh, it's 0 gigabyte. And it is also missing the address of the remote server, and the status code is also missing. So this is an example where you're trying to debug like issues with an application, but where the application is like failing to provide sufficient information. So this was the first attempt. The next attempt is to use something like Wireshark. Wireshark is basically like capturing all like network traffic and provides like evidence that something is wrong. If something's wrong, it's been captured, then you can definitely be sure that, okay, whatever I found, it's basically the truth. So remember what I said before. I saw it was HTTP2 as protocol. So in Firefox, you're limited to the application layer. So you typically only see these like HTTP requests and responses. In Wireshark, you're looking a layer lower at the network layer. So aside from this application data, you will also see all like the HTTP2 framing and the TLS layer on top of that. So and all of this is of course encrypted. The application has access to the secrets to encrypt the data, and the application that's hidden to the website. In Wireshark instead, you're looking at the outside application, and all data is encrypted. So in order to decrypt this, in order to like access this HTTP request and response that we would otherwise see in the web developer tools, we need to capture all packets, including the initial TLS handshake. Why is that important? In the initial TLS handshake, the session keys are actually negotiated. So if you're missing that, if you're just starting the capture while you already have a website open, you will, in Wireshark, you will only see application data, but it won't, since you have not captured the like handshake, you won't be able to make any sense of the application data. And of course, we need to capture the secrets that would enable decrypting the traffic based on, well, the secret and the handshake. So remember, something like Firefox, like the web browser or the server, they use this handshake combined with like their own in-memory keys in order to compute the session secrets. And these secrets is something we need to get from the application. So, so with this in mind, we need keys, we need packets. So, in order to avoid like getting overwhelmed by like by a lot of packets, it's definitely a good idea to set a capture filter. So, if you haven't like used Wireshark, like some of my colleagues, like they haven't, if you start Wireshark, this is basically what you see. If you are on a VPN, it's important that you select the right interface. So by default, Wireshark will try to guess whatever interface you have. Typically, we'll pick, for example, the wireless interface or the Ethernet interface. And based on macOS, you have like a lot of interfaces with names like EN0, EN1, and they might not make sense at all. So you can then use these spark lines as a hint where the actual traffic exists. If you start capturing if you connect to a VPN and capture like on your wireless interface, you will only see the like encrypted VPN traffic, which is not useful at all. If you're trying to debug like this web server, you should instead select the right interface. So having that said, you first have to select an interface and then change the capture filter, not the other way around, because the capture filter is specific to an interface. And as capture filter, you could, for example, say host bugs.wireshark.org, because I was having an issue with exactly this site. Or you could limit it to a port number, for example, TCP port 443. Or you could combine both. You can find more details in the pcap filter manual page. The whole like capture filter language is described there. Don't confuse it with the display filter field. So I see some people who are new to it to like enter a capture filter in display filter field and all the way around. The display filter field, they apply to basically the dissection process. So you start with the capture process, which is right here. In the capture process, you can decide to drop packets. That's the only thing you can do with, well, a capture filter. After having captured the filters, you'll get a whole list of packets, and to make it easy to digest that list, you can set a display filter. So that's why I call it display filter. It just hides some packets which you already have in your capture file. And well, once you like select the right interface, optionally entered capture filter, you can start capture with Control E or Command E on macOS, or by double-clicking the interface. So that's the package part. Now we still need the secrets. This is a lot, but basically the idea is you set an environment variable called SSL keylog file, and you have to do this before starting Firefox or Chrome. The reason for that is that this environment variable is only interpreted during startup. If you already have Firefox or Chrome running, and you, try to start Firefox or Chrome with this environment variable, it will just see like, oh, I already have an instance open, I'll just, do nothing anymore. And then this variable won't be applied and the keylogging won't be enabled. So what is this keylog environment variable? It points to a path of a file which will be created if missing, and if it already exists, keys will continuously be appended to this file. So I will demonstrate that now. So on Windows, on Windows you could set environment variables like globally, but I would not recommend that because it's very easy to forget that you have enabled the setting, and it actually like logs all keys from all your web browsing activity. For example, if you're like banking, it might still get logged, and that could compromise your data. So that's why I prefer to create a script where I set an environment variable, like set SSL keylog file equals whatever path I have. So I create something on the desktop, and then I run start Firefox. This could also be something like start Chrome, and Windows will start the right file. So that's my file. I will start it. Actually, no. I'll start with start Wireshark first, because if I start Firefox first, then I might miss this initial TLS handshake I mentioned before. So it's important. First, start Wireshark, then capture filter. Well, I would probably just capture everything. This is the interesting interface. And now I will run Firefox with the keylog file setting. Let's see. It's not working. So why it's not working? Start Firefox, SL keylog files. Perhaps I already. Oh. What version of Firefox am I using? There is one known issue with the latest version of Firefox where it would not write keys. So this mechanism used to work for Firefox and Chrome, but starting somewhere in Firefox 65 until 67, it has been disabled due to some bug. But it should hopefully be re-enabled in Firefox 68. Let's see. Perhaps I should remove the quotes. Okay, let's try it again. Okay, apparently the quotes matter. So without quotes it is. Let's see. So let's close it again, remove this file. Start Wireshark first. Select the right interface, start the capture, and start Firefox again. For example, if I now go to, I can type bugs.wireshark.org. Why do I have two? I filled for TLS. I should see my Firefox activity somewhere. I could enable name resolution, and then I can use a filter like ip.host equals bugs.wireshark.org. If I don't make a typo. Oh. That didn't exactly work. Oh. The reason for that is probably because the Wireshark domain, it's on a shared web server. So if you resolve the IP address to something else, like try to resolve the IP address, I might get a different host than the one I try to visit. So instead, I'll try to look up the connection through the TLS server name field. So in every client hello, there is a name, the server name, and that's sent whenever you try to make a connection. This makes it possible to support virtual hosting. So let's try to prepare a filter, because I don't remember this field name by heart. So, and now I can use something like bugs.wireshark.org. There you go. What I typically also do is I include the stream index in the TCP layer, so I can easily identify different connections. So apply as column, that is, or I could just like drag it, that would also work. Oh, except I can do it during capture, anyway. So 67, 66, 67, so I can try to limit my captures, TCP.stream in 67, 66, 67. And since I have a lot of ACK messages, I'll probably try to restrict it to application data. So yeah. All right, so let's see. So right now I showed you how to configure the environment variables so that the file gets logged. I haven't shown you yet how to actually use it in Wireshark. But let's check the content of the file first. The content of this keylog file is it's a text file with on every line unique per session secrets. So this secret is specific to one TLS handshake and cannot be reused for other sessions. The form for TLS 1.2 and before, you basically have a client random and then some identifier from the client hello, plus the master secret. And this master secret enables further decryption of the session. In TLS 1.3, the whole key schedule has changed, and there are many more keys which improve security. And that's why we have a lot more client handshake traffic secret, handshake traffic secret for the server, and likewise the traffic secret. So in TLS 1.2 and before, the single master secret is used to encrypt the application data. It's used for session resumption. In TLS 1.3, there are different keys for session resumption, different keys for the traffic encryption, and in TLS 1.3 the handshake is also encrypted, which was not the case in TLS 1.2. So that's why you have a lot of keys. Yeah, any questions?
Are all of these exported by Firefox or Chrome, or are these different programs that might export the different formats?
So the question was whether all of these lines are exported by Firefox or Chrome. This format was originally defined by, I think, Adam Langley from Google for, I think, for Firefox, and it was later also ported to Chrome. Actually, these secrets are exported by the TLS implementation, the TLS library that provides the TLS functionality. So the TLS library that backs Firefox is called NSS, and the TLS library that backs Chrome is called Boring SSL. So any application using these two libraries can potentially create these files. And lately, in case you're interested, OpenSSL has also gained an API to create this kind of format. But basically, this has been like a de facto standard.
I have a question for you, Peter.
Yeah.
In a single TLS like 1.3 or 1.2 session, will the keys change mid-session? Ever?
So the question is whether the keys change mid-session into TLS 1.2 or 1.3 session. The answer is for TLS 1.2, with the renegotiation, you basically get a whole new handshake, and then the keys would change. But that would also, due to this like new handshake in TLS 1.2, you will also like log a new line. In TLS 1.3, there's something called, on the protocol level, there's something called key update, but it basically takes this like traffic secret, and then it will derive a new one from this one. So if you know this initial secret, that's why it's called like traffic secret 0, you can derive like traffic secret 1, 2, and so on.
Will that show up as like a cipher, a change cipher spec note?
No, in TLS 1.3, you don't have change cipher spec messages. I think it's like a handshake message, which is a key update. So you can tell it on the wire, but it's not a change cipher spec message.
And how long, once we capture these keys, how long would they be valid?
So these keys are unique per session, and these are indeed valid for the lifetime of a session. Yeah, the reason is, so these keys are not actually directly used to encrypt data, but these keys are used as a base key to derive new symmetric encryption keys to encrypt data. Thanks, great questions. Let's see. So I showed you how to write this key log file in Windows. With Chrome, you can also use the --SSL keylog file parameter. This might be helpful if you're trying to create a shortcut rather than, say, a batch file. But do remember this SSL keylog file name also still works with Chrome. And I found that this path had to be absolute. If I use a relative path, it would not work. And on Linux or on macOS, you can also create like a one-liner to pass this environment variable to the process. And typically for reproducing issues, you probably have already like your web browser open, and you might not want to like close it. And that's why it would be useful to create a new separate profile, which I will also demonstrate. So this is my like main Firefox instance. I don't want to capture, I don't want to close my session, but I still want to reproduce something with Firefox. What I could do is Firefox, no remote, SL keylog file. And then, for example, keys.txt. I don't have keys.txt. And then dash profile, for example, temp Firefox. But I still have to create this temp Firefox folder first. That's specific to Firefox. So with Firefox, I have to create this profile folder first. And then I can create a new browsing session. So this is completely separate from my own session, and this is very useful if you're trying to isolate an issue to a web application. Now, I can close this. You'll see now I have this keys.txt file. And what's in there? Well, exactly what you would expect. A lot of TLS 1.3 traffic, some 1.2 traffic, and so on. And Chrome has a similar option, except that Chrome will create this directory if it was not already existing. I said before, this SL keylog file environment variable is interpreted by the TLS library. So NSS supports it, BoreaSL supports it, and curl also has support for it built in. And it's very useful because developers use curl very often to test API calls, and being able to record this API call is very helpful. So just to show that it works, keys2.txt. I'm not very creative with names. So let's see, example.com. So a lot of data. So that was the command. And I should have keys.2.txt. And this looks like TLS 1.3. And if we scroll up a bit, we can also see that in the verbose output of curl. So this is how we get this secret. How can we actually use it? We go to the protocol preferences of Wireshark. So if you have, there are two ways to get there. If you already have a TLS layer selected, you can like right-click on the TCP layer. TLS layer. Go to protocol preferences and directly select, change the setting here. Alternatively, you could go to like edit preferences and go to protocols, TLS, and change the setting. Note that, yep.
Just to note that that protocol preference changed in 3.0.
Right.
It used to be SSL, and we've all moved the SSL stuff to TLS. The documentation is lagging a little bit behind.
Mm-hmm. So indeed, in TLS,
Like 20 years.
yes. So the protocol in Wireshark was called the SSL before, and now it's TLS in 3.0, as Graham mentioned. So I'll select my keylog file here. I had this on desktop, and I think I called it keys.txt. So note I have application data here, and there's no decrypted TLS tab there. If I now press OK, there's now a decrypted TLS tab right there. And I can recognize a lot of stuff. This certificate, I guess. Oh, just the handshake. But as you can see, there's TLS and HTTP on top of that. So this is how you enable TLS decryption in Wireshark, and how you can verify that decryption basically works. If you are using T-Shark, or if you would want to quickly be able to change between keys, for example, you have a lot of capture files and a lot of different keylog files. Going through this GUI is very boring, and you can also use this -o tls.keylog_file set flag to specify your keylog file. This is exactly the same as that one. And with the -r option, you can specify a capture file to read. And T-Shark is the textual version, the CLI version. So with this in mind, we were able to decrypt the trace, and we noticed the headers had content length 213, but the actual data was 225 bytes. That was basically the 5 bytes that I removed from the file. So for some reason, Firefox didn't update the content length header. It was still using the old value. And that's also why, probably why the Cloudflare Edge was throwing a very big white error page. That's probably a fallback of some kind.
So just to be clear, that you originally attached the file with a length 230, edited it so that it was slightly shorter, but Firefox had retained that initial file length.
That's correct. So indeed, so to repeat what you said, Firefox, the initial file, the file length that's reported there is based on the initial file that was selected, not on the actual file that was included, was uploaded. So. Yeah, and you can also, yeah, okay. So now we have reproduced our issue, our bug, and we would like to create a bug report. So what do? We include the step to reproduce, the environment, and so on. But now we also want to share our packet capture because it contains the proof. And we also need some decryption secrets because that enables you to decrypt that packet capture. passing around like a packet capture and a keylog file it's quite difficult. It makes distribution difficult. You have to send 2 files at a time, and every time you change between packet captures, you have also to change your key file. So that's why in Wireshark 3.0 we added a new feature. You can now actually embed this keylog file in a packet capture file. And there's no GUI way to do that. You have to resort to the CLI tool called editcap. And basically, you call editcap with the -- inject -- secret option, TLS, comma, then the keylog file, and the original file, and then the output file. As convention, I generally add a DSP suffix to it. DSP stands for decryption secrets block, which is the technical thing that enables this functionality in the pcap and gfile. And I highlight pcap and gfile because this is indeed something very specific to pcap and g. It's not supported by the libpcap format or other vendor-specific formats. In order if you use the inject secrets option, by default it will add to whatever secrets already exist. If you are trying to sanitize a packet capture file, trying to remove some secret, you have to use the -- discard all secrets in addition to this. One potential use case is you're capturing basically all packet of your system without a capture filter, or you still have a lot of different sessions and your keylog file is very big. Including that keylog file in a packet capture that has been shrunk by a display filter, that could potentially leak more data than desired. So what I would do is use T-Shark to extract. So let me put it in a different way. What I would do is try to reduce this keylog file to the bare minimum that's actually needed for decryption, and that's what this inject TLS secrets script does. So yeah, basically you call it with the original keylog file, the input file, and output file. If you omit the output file, it will infer something like som-dsp.pcapng. And under the hood, it uses T-Shark to only extract only match client hello messages and extract the random field, because this random field was used in this keylog file to map to secrets. Remember, you had something like client random, the random field, and then the master secret. This random field is designed to match that second field, that second identifier. And then basically there's some processing in order to eliminate everything that doesn't match. And in the end, it calls editcap with this discard all secret option and all the other options as you would expect. Yeah, and I put the link in my slides, and which will be published later. So yeah, I can also just show you how it works. So let's see, where's my script? Okay. So I have my fx upload 2.keys, which has 61 lines, but fx upload 2.get. And here, for example, I want to okay, that's not important. So let's have a look. This was my original packet capture file. And I wanted to only extract the bugs.wireshark.org traffic. So that was server name, I think. Okay. Okay, so I have only one packet. Let's see, follow TCP stream just to match the whole packet. As you can see, like this option has changed to basically match this one. This ensures that all packets related to this session are matched. Now I can save this session, export specified packets, only the disk page versions, and this is my limited.pkapng. So now I have my limited.pkapng, and I also had my original key file. And let's see, this is my inject script. So I provide the original keys file, which was called fxupload2.keys. I provide my new limited packet capture file. And now it's, as you can see, it only injected 5 secrets. Now, what are those secrets? Well, we can also check the resulting output file. So, as you can see, decryption works. But how can you know where, like what kind of secrets are stored in there? For that, we have to use a kind of exotic feature of Wireshark, which is called reload as file format or capture. If you do that, then it will show you the raw structure of the input file. So you get a single record, and it's the pkapng file. You get a lot of packets, and the actual secrets are in the decryption secret block. So that's why I add this DSP suffix. And if you do something here, right-click and do show packet bytes, you can indeed see these are the. This is the data that was stored. So 5, like 1, 2, 3, 4, 5, exactly 5 secrets as was reported.
Can you track that 5.sh file?
Sorry?
TLS, inject TLS secret .sh. Can you track that?
Where's that? This one?
The secrets.sh. Inject TLS secrets.sh. Can you track that file?
Show the contents of the file. Well, that'd be
Oh, okay. Well, that one was the one I showed on GitHub.
Oh.
Like that's the same, yeah. This is like that GitHub repository. Okay. So yes, so this makes it really convenient to share packet capture file with the secret embedded, and a lot of people are very happy with that. But yeah, that's basically like how we as developers work. Like I ran into this issue where I continually had to, for example, copy the keys from the packet capture comments, or I have to manually like change this keylog file, and it was getting a bit annoying. So at some point, I was like, okay, I'll try to follow up with this feature request.
Does that work with Wi-Fi decryption as well? Injecting secrets?
Decrypting, so is your question whether it also works for Wi-Fi?
Yeah.
No, it has not been implemented for Wi-Fi. There were also suggestions to do something like that, but concretely for new secrets, like any new secret block that's added to the pkapng format has needs some kind of identifier to be able to link the secrets to whatever session or association or protocol specific thing you have. I don't know exactly how you would match it to Wi-Fi, but perhaps someone else with more 802.11 experience could implement that.
You could match it to the 434L keyframe and tie it to the MAC address of the sending MAC address. Would that work?
It would. I mean, again, I'm not a great 802.11 expert, so I can see how it can be done. It's just like all these, you've got to find somebody with the knowledge and the skills and the time to do it.
So yeah, so basically someone with experience with 802.11 could implement it, yes.
But right now, it doesn't seem to be possible to export the encrypted data.
So you'd like to export the encrypted data without the TLS layer and so on? Or So you're asking like where it's possible to include decrypted data with the PKG file? No, that's not possible. Like right now, Wireshark has to interpret it, have the appropriate secret to decrypt stuff.
The reason why that would be useful is a lot of cybersecurity tools take PCAP. And so they could take encrypted data. And so if you give them PCAP-NG, they would have to run Wireshark to process it. And you can spit out the encrypted data as PCAP. But a lot of cybersecurity tools can actually analyze it.
So it depends. So do you care whether the original packet capture was whether the original packets are still in the PCAP-NG file?
I don't. I can see how that could be useful.
So Wireshark has a feature okay, that doesn't work for HP2, but that has a feature exports PDUs to file, and that would like work for HP, and then like all layers above HP, like TLS, IP, and so on, they would be stripped, and you only have the HP packet remaining. I can try to find an HP capture, I guess. Let's see, do I have H? So this is something, okay. So I'll try to extract the HP here. So follow stream first.
Oh, you did the follow stream, yeah, but that's no longer the stream. That's just the data.
That's just data, but I'm using follow GSP stream to identify like the stream that contains the data. So this stream 66, and this is like the data that could potentially be exported.
Right.
Now, if I go to File, Export. I should probably stop the capture first, otherwise I can't use that functionality. Export PDUs to file. I believe it works like this. Is correct, Graham?
I've only used it once or twice.
Yeah, so there you go. So as you can see, I started with like a TLS capture with HP and stuff on top of that. Then I did file and export PDUs to file. Thank you. And here I selected OSI layer 7 because HP is in layer 7 protocol. Typed HP, pressed OK. Then I got all decrypted data out of it.
Does it still maintain the layer 2 and 4?
No, those are lost.
Yes, okay, so yeah, there's an equivalent to do that in T-Shark also. The request would be to also maintain the session, so the tools can correlate the TCP session to the decrypted data.
So as you can see here,
Basically,
some.
write to the capture file, and it's difficult. So don't hold your breath.
So your question, just for the recording. So your question was whether this kind of functionality could be implemented in T-Shark while also relating to the original packets.
Original session, yeah.
To the original session. So inside the metadata, we have like a source IP address and port number, so on. So you could in theory, you could in theory link it to the original packets that way.
And what file format is that exported at?
This is the Wireshark specific exported PDU format. So I don't think it's even like standardized in the TCP dump like specification. So TCP dump maintains a list of all kinds of link types. I don't think this format is specified there, but it's supported by Wireshark. Yeah. As this format is also what we use for like fuzz testing. So when we rely on Google OS fuzz to fuzz out dissectors as well. And whenever they find the issue, there's a script that converts their like raw blob of packet data to a capture using these fields. So that was just the most convenient approach. If you have like a client like Firefox or Chrome or like curl or a web server where you can get these secrets from, it's very convenient. But you cannot always do that. For example, Internet Explorer is not able to dump these secrets, or Perhaps you don't have the possibility to continuously get these secrets. In those cases, you can try to use RSA private keys. There are quite some limitation with RSA private keys, so it's only possible if you're actually, well, the server administrator who has access to this key. If you're, say, a client and trying to debug an issue with, say, some AWS API from someone else, well, good luck. That's not going to work. It's also not working if you don't have the right ciphers. So TLS has like many different cipher suites, and these cipher suites control what kind of key exchange algorithm is used, what kind of like symmetric key encryption algorithm is in use. And this part, the ECDHA, that's the one that refers to the key exchange. And RSA private keys can only be used to decrypt key exchange that use, well, the RSA key. And ECDHA or DHA, they use a mechanism, well, that basically you cannot get the secrets even if you have the RSA key, because in those cases the RSA key will only be used for authentication, basically like signing the handshake and proving to the client that, hey, I actually own the private key that belongs to this certificate. It also doesn't work with session resumption. I'll show you why. So now let's just to get, like, deleting everything is not necessary, but it's just more convenient, as in less data to work with. So let's say I'm only interested in example.nl. And let's start my capture, example.nl. Now I close it again, and because I close it again, the connection is also terminated. Let's see. So as you can see, I have a client hello somewhere, and well, I guess it got closed at some point. Now I go to example.nl again. And now, because I recently visited this website, it's still, the session is basically still cached by Firefox. Now, if I try to look up the server name, example.nl, am I lucky? Maybe. Well, there are many different sessions. So I will just select them and color them to have easy way to identify them. So I'll press Control 1, Control 2, Control 3, Control 4. Oh, 3, 4, 5, 6, 7, 8. And these are basically shortcuts for colorize, let's see, the colorize conversation, I believe. If I press like Control Space, it will clear everything, like all of them. Now I'll try to prepare a filter based on this. I'm fine with matching everything, but I just want to see the TLS data. So here's my client hello, server hello, certificate. So here you can see there's a key exchange going on. This is TLS 1.2. So both sides will typically try to send key exchange messages to each other. So 0, this is the very first session. Now I try to locate the second one. So second, it's continuous there. Oh, this one is also not resumed. Okay, fourth. So now I look at where there's a large time gap, because here I close the session, and here there's supposed to be new session. So client hello, server hello. As you can see, there are no key exchange messages for this session. And these key exchange messages contain like the secret that's well, basically the secret where this RSA key is used for. So the key exchange message contains, well, some random data, that's the key. And the RSA key can be used to decrypt this. But if this key is missing, then, well, some a tool like Wireshark won't be able to guess the key unless you somehow like passed it before.
One question.
Yeah.
Right now, we are able to capture the keys where the browser is involved, right?
Right.
If I wanted to capture encrypted traffic between two servers where I do not have a client in the browser, how do I capture the in between two servers?
So the question was, if I have two servers instead of browsers, how do I capture the keys of those? So if you have a server that uses the OpenSSL library, there's a script available to basically inject code that ensures that the keys are dumped in the same way. I can.
Does it work for DHE as well? DHE, if it is using the DHE algorithm?
DTLS?
DHE.
Element exchange. Yes. Yes, if you persuade OpenSSL to cough up the secrets, then
Yes.
it will work.
So
Pre-master secrets.
So yeah, so the RSA, if you have the RSA key, it will try to decrypt the secret from the wire, from that message. If you have this like keylog file message, it already contains the secret that's like embedded in that file, basically. To be, well, technically precise, that message contains a pre-master secret, and from this pre-master secret you can derive the master secret. And the master secret is the thing that gets logged in the keylog file.
So that I can use in Wireshark.
And that you can use in Wireshark, yes.
Things like Windows applications, you can't get S-channel
Right.
to dump the pre-master secrets. So
Yes. So Graham mentioned in Windows, like S-channel is the standard library. I did some brief research. I haven't like completed, but it seems possible to like obtain the session ticket keys that are used to to encrypt the session ticket that are actually visible on the wire. So maybe it's possible to use those session ticket keys to decrypt the session ticket, and that way obtain the secrets to decrypt the whole traffic. But it's just a theory, no. So nothing production thing worthy yet. Let's see. Yeah, okay. So at the end of the slide, I linked to an earlier presentation of mine where I actually mentioned a method which you can use to get secrets from services that use OpenSSL and some other libraries. But for this presentation, I thought, well, I will try to limit to a scenario like this. So yeah, if you have the RSA private key, one advantage of this is you have to configure it only one time, and then you can decrypt all data using the RSA key exchange, that is. One scary thing about this is if you leak that private key, all future and previous data will be compromised. An attacker with that key can also decrypt that. That was a bit scary thing. So in Wireshark 3.0, we added a new feature. So previously, you could configure RSA private keys in the TLS protocol preferences. Now we added a dedicated section to the preferences section called RSA keys. This could potentially be used for other protocols, but for now it's just limited to TLS. As before, you can add a new key file. And unlike in the previous dialog, you had to specify a lot of fields which were not used at all. For example, address, port, protocol, file name, password. In this new dialog, you only have to press this button, provide a file, and if a password is needed, only then it will ask for it. So that's why it's this interface has been simplified. As before, this can only accept passwordless like PAM files. So basically the files with -- begin private key or something like that. Or a PKCS12 file, which is a password protected container for private keys. The new thing about it is you can now also like configure a PKCS11 provider Those providers, PKCS 11 is a standard interface, like programming interface. So applications like Wireshark can like talk to it, and it's up to a vendor of a specific like HSM or like USB token to provide the necessary functionality. So Wireshark will basically ask, for example, your USB token, hey, can you decrypt this key exchange message? And then the token should decrypt it and provide you with the master secret. That way the private key never leaves like the token or HSM and will never appear on your system. So that's something that's probably valued by environments that handle very sensitive data like banks or healthcare. Yes, so those tokens are a bit technical at the moment. They like look very long. This has been tested with basically a software HSM. If you plan to use this and run into the problems, like let us know because, as I said, this is just like a standard programming interface. The actual implementation is very vendor specific. Also, now we have seen like the basics of how you can like do TLS decryption in Wireshark, but there are some things to be aware of. So by default, Wireshark doesn't enable reassembly of out-of-order TCP segments. What does that mean? If you receive a TCP segment with a sequence number that doesn't align, you will see something like TCP preview segment not captured, followed by TCP out of order. But those should be reversed. And by default, well, that is not done, and decryption will fail afterwards. So you will see it's something like ignored unknown record or the garbage. And if you are doing application layer debugging, I recommend you to always enable the reassemble out of order segments option, which was added to Wireshark 3.0. The reason why this is not enabled by default is because there are environments where actually like segments can be missing. For example, if you have a 802.11 capture, it's possible that you have like a huge gap within a stream due to, say, bad packet reception, but you might still be able to interpret it, to partly interpret the data that is available. If you enable like this option in case where you are missing packets, then you won't be able to make sense of the whole stream. And also, in some classes, you might be told to disable, reassemble TCP streams if you're, for example, doing TCP analysis. You have to keep that enabled. Mm-hmm. Another issue that some people run into is if they have very large certificates or very large like certificate request messages, then Wireshark would briefly show something like encrypted handshake message in the middle of the handshake. So usually you have like serve hello followed by certificate and some other messages. So this is kind of odd. Starting with Wireshark 3. The reason for this issue is Wireshark wasn't able to like reconstruct handshake messages that were split across the wire, across records, that is. So starting with 3.1, it will be fixed, and you will actually see something like certificate fragment, and the whole certificate will be reconstructed at the end. So here you see there are two fragments. So something in there and something in there, and the result is shown next to it. If you're developing a new protocol that uses TLS, for example, if you're trying to develop NTP over TLS, which is currently in the draft, you might run into the problem that the port is already used for other purposes. So by default, if you run TLS on like an unreserved port number, Wireshark will be able to detect like, hey, this is TLS. I'll try to interpret it as such. If you are trying to use TLS on a port that is already used for different purposes, for example, 123 is used for NTP, then Wireshark will try to interpret this as NTP. In those cases, you have to explicitly add an override so that Wireshark will try to dissect it as TLS, for example. And you can do that by like right-clicking a packet, decode as, select tcp.port. This will usually be populated, and this will be a menu where you can select between the source and destination address, and here you can like pick your protocol. In addition to that, there are many potential applications possible inside the TLS tunnel. Wireshark will use the ALPN extension in the client hello. So applications might advertise like, hey, I'm HTTP2. Well, I'm expecting HTTP2 or I'm expecting HTTP1. Wireshark will try to use that if available. And otherwise, you have to also explicitly provide a hint there. So just, are there any questions so far? Okay. Otherwise, I will just get into another scenario. So, so far, the server name has always been like public, like a leaked. If you look at the TCP stream, for example, you will see that the handshake is always shown. Let's see. Okay, let's try that for a start. So if I try to follow this stream, let's see. Follow stream. You see, okay, this is the server, the server name that's leaked. So if I select there, this is a like well-known server name indication extension. And in TLS 1.2, the identity could also potentially be leaked through certificates. In TLS 1.3, this certificate is also encrypted. So that means if you want to well hide this, you probably have to encrypt it in some way. But since no like connection has been established yet, you need to get the key in some other way. The way that's done with ESNI, so basically where you encrypt the server name, you try to query this key from DNS, but not just like plain unencrypted DNS, but you get it from, for example, DNS over HTTPS or DNS over TLS. So basically, the connection to a DNS server is encrypted. You try to get your keys from that DNS server and then encrypt your server name, and that looks like this. Let me try to configure this keylog file. So as you can see, this was an attempt at Firefox, like Firefox properly configured to use ESNI. Right now, only Firefox implements draft 1 of ESNI, and I think only Cloudflare implements a draft 1 as well. I'm not aware of other providers that implement this experiment. So this client, hello, it's the original DNS server. So this is, well, still in clear text because you have to start somewhere. If I try to like enable name resolution, it will probably become more obvious. So this is the DNS server. So there will be a handshake in TLS 1.3. And after that, there's a DNS over HTTPS query. And this is the body basically. So basically, I'm trying to ask for the address of example.com. And then I get my response. So now I know what kind of like IP, let's see, what kind of server to connect to. Oh, let's see. Oh, actually, I think the first query example.com was maybe just a probe to see whether things are working. So here I was actually trying to access bugs.wireshark.org. Yeah, so Firefox tries to send a query, gets a response, and now knows what address to connect to. So it tries to connect to the address, and in this client hello, if I do follow TCP stream again, I don't see Wireshark.org, do you? And why is that? If we expand it a bit, we'll see, let's see, encrypted server name. So there's a whole like new TLS feature where the server name is encrypted and it's no longer visible on the wire. And as you can see, the certificate is also encrypted. So if I select the certificate, you'll see that this has been encrypted. And this is basically on a high level how encrypted SNI works. You try to get some key through like a trusted channel with the DNS server, and then send an encrypted version of the server name in place of the unencrypted version. So I'll quickly go over quick as well. Yeah. So as you might know, there's like a new standard called Quick. It was already developed by Google, but the intention has been always to like standardize it, similar to what's been done with HTTP2 before. So HTTP2 started being like with Speedy, developed by Google. It evolved into HTTP2, and well, it has been like a final RFC since for maybe 3 years already, something like that. Quick is probably going in a similar direction. So while HTTP2 is based on TCP and TLS, Quick will be based on, well, UDP. One of the advantages of that is to avoid the head-of-line blocking problem. So HTTP2 and Quick both have the concept of multiple like streams inside a single connection. But with TCP, if you lose just one packet, then all streams will be blocked. And that's called the head-of-line blocking problem. With Quick, you have multiple independent streams, so even if one piece is lost, streams that are fully received can already be processed. And why I mention this, what's the relation with TLS? Quick uses the TLS like handshake protocol. So all keys you saw in that keylog file before also apply to Quick. There are like many different implementations of Quick available now, and some of them also are able to generate a key file, which makes it possible to decrypt stuff in Wireshark. So how does that look like? Quick 19. I'm not sure if is it visible? Not sure. Small. Okay, I'll use this interface then. So, in the major, like one big thing about Quick is everything is encrypted. So in TLS, you still have this client hello with a lot of unencrypted stuff. In TLS, the whole thing is encrypted, as you can see. So this has been decrypted. Note though that this initial message is like encrypted with a fixed key. So what this means is if you're just trying to perform like a regular expression search on some data stream, you will not be able to understand Quick. You actually have to implement Quick in order to decrypt this stuff. So yeah, I think that's where I have to stop. That's like the main takeaway of Quick. Everything is encrypted, and it uses TLS for its security. So today I showed you how you can use a keylog file to enable decryption in Wireshark, how you can embed the secret in a single packet capture file for easier distribution. There are a couple of preferences you have to take care of in order to avoid edge cases, and always use the latest version of Wireshark. I had a coworker who was still using 2.6 something, and was like, "Hey, this doesn't work." And then, well, after he upgraded, suddenly things worked again. So, and also for you, if you want to know more about decrypting traffic between these servers, have a look at the prior presentation. So, are there any questions? Thank you.